Okay, moving right along in our journey through 1324. In section 3.4, we focus on our quadratic functions. Now, quadratic functions, this is one of our families of functions. The parent function, f of x equals x squared, is that parabola that sits at the origin and opens up just so. It's a second degree polynomial function. The domain of our quadratic function is all real numbers. That's the domain of the parent and every quadratic function. Remember, once it starts all real numbers, it stays all real numbers. The range of the parent quadratic function, that range of y values, function values, as I move from negative infinity up, my range starts at 0 and it continues to positive infinity. Because my range has a limit, this range is going to depend on where my vertex sits for any child function, any other quadratic function other than the parent function. I cannot guarantee that the limit will be at 0 or even that it opens up. Now, we've been given an example quadratic function. I want you guys to go ahead and put the arrows on the ends because that should continue forever in both directions moving up. I can see immediately that this is not my parent quadratic function. And I know it's not my parent quadratic function because the vertex is not at the origin. The vertex is down here. It looks like 1, 2, down 1. So my vertex is at 2, negative 1 instead of at the origin. I see that I have two x-intercepts where my graph intercepts the x-axis and one y-intercept. A function has to pass the vertical line test, so it will never have more than one y-intercept, but depending on the shape of the function, it could go back and forth around that x-axis. It can definitely have more than one x-intercept. So let's start filling in these characteristics. I have two x-intercepts. I have one here at 1, 0 and another at 3, 0. My x-intercepts will always happen where y equals 0, because I haven't moved up or down from the origin off of the x-axis. The y-intercept will always happen where x is equal to 0. So I don't move left or right away from the origin, but I move up or down. In this case, my y-intercept is at 0, then up 3. So 0, 3. And notice that I've given my intercepts as ordered pairs. I want it that way most times. My math lab is not as picky. We already said our vertex is over here at 2, negative 1. That vertex is that turning point for my parabola. Is this vertex a maximum or a minimum function value? Well, it's as low as it gets, so this vertex is a minimum function value. The minimum function value, the function value is the y value, so the function value is negative 1. And it occurs where x is 2. But the minimum value is that function value, that y value, negative 1. The axis of symmetry is the line, in this case a vertical line, where I could choose to fold my graph, fold my parabola for this function, and the sides are going to match up. It's the mirror line. Well, my axis of symmetry goes through that x value 2, and in fact it's a vertical line, so the equation is going to be x equals 2. An axis of symmetry is a line, and so I always write it as an equation. Vertical lines are written as x equals. You don't just say 2 because that represents a point, not a line. So it's x equals 2. We already said all quadratic functions have a domain of all real numbers. Once it starts as all real numbers, it stays all real numbers. Our range has a limit though. Our parent quadratic function has a range with a limit of 0, but this function has been shifted down. So the range for this function starts at negative 1, not at 0, and goes up forever. So the range here is from negative 1 to positive infinity. And then finally it asks about transformations. If my parent function, this parent quadratic function, sits here at 0, 0, there's my parent, f of x equals x squared. And my transformed, oh, I just messed that up. I'm so sorry, guys. I'm going to see if I can erase this. As I drew it, I realized, oh, that was not what I meant, where I meant to put that. Let's see what we can do. And let's see if I can get my, there we go. Hopefully you are all sitting there having realized what I did. I got in a hurry and was talking, and this is my axis of symmetry. Axis of symmetry, and I was not paying attention and took it as my y-axis. My parent function should sit over here. There we go. F of x equals x squared. There's my parent function sitting on the y-axis, not on that axis of symmetry. So here's my parent function. My parent function sits here at 0, 0. I have transformed this function. I've moved it to the right 2, and I've moved it down 1 to get it to where it is. So that's my transformations. To the right 2 and down 1. Because I know those transformations, I can write the equation for this function, this transformed function. My pattern of transformations, I've got f of x equals, we go over 1, up 1, over 1, up 1. 1 squared is 1, so we haven't changed how wide it opens, so we don't have a coefficient out front. X minus, well, we move to the right 2, so there's my horizontal shift. This is a quadratic function, it's being squared, and then it went down 1, so minus 1 out here. Remember that my pattern of transformations says that it starts as x minus h, and then I have my whatever the function is and plus k. So my horizontal shift always starts out as minus that horizontal shift, and then the vertical shift goes the way I expect it to. So this is the equation for this transformed quadratic function there. Alright, quick review down here, finding intercepts. To find the x-intercepts, I set y equal to 0. To find the x-intercept, I set y equal to 0. So my x-intercepts are going to look like, not that, thank heavens for whiteout, some x value that is not, and then y is 0. So this is the value I'm looking for, x-intercepts right there, where y is 0. And you can have multiple x-intercepts. You don't just have to have one. Y-intercepts happen where x is 0. So my y-intercepts, the ordered pair, are going to look like where x is 0, and then I got to figure out what y would be. And I only have one y-intercept if it's a function. Now this is the general set of steps. General info on how to find intercepts. So if you've been struggling with finding your x and y intercepts, there you go. Okay, let's look at the next page. We are going to graph some transformations of functions along with, notice it says with its parent. Well, here's my transformed function. I see that I'm squaring it. So the parent function is y equals x squared, or f of x equals x squared. There's my parent function. So let's go ahead and color code this. My parent is going to be y equals x squared. It's going to be in green. And then I will do my transformed function in purple because I like purple. Alright, my transformations, I've got two transformations here. I've got a horizontal shift and I've got a vertical shift. My first question says, does the parabola open up or down? Well, it's positive out here, so just like the parent opens up, this transformed parabola is going to open up. What's my vertex? Well, my vertex is my horizontal and vertical shifts away from the origin. So this is at x plus 2. Remember, it goes the opposite way we expect it to because it starts as x minus h. So I had to have plugged in a negative 2 there. So I've got negative 2, negative 9 for my vertex. So 1, 2 to the left, and 1, 2, 3, 4, 5, 6, 7, 8, 9 down. There's my vertex. Negative 2, negative 9 for my vertex. I know it's going to open up, so I'm going to have two x-intercepts. I also have a y-intercept. My y-intercept happens where x is 0. So let's see what happens here if I plug in 0 for x. So if x equals 0, where do I want to do that? Y equals 0 plus 2 squared minus 9. Well, that's 4 minus 9. Where x is 0, y is going to be negative 5. 1, 2, 3, 4, 5. Does that make sense? It does. Our parabola is going to open up, so it can go through that point. X-intercepts happen where y is 0. So to find my y-intercept, I plugged in 0 for x. To find my x-intercepts, I'm going to set y equal to 0. So I've got y equals x plus 2 quantity squared minus 9. Let's go ahead and do this part. It's going to be the easiest way to do it. X plus 2 quantity squared is the same thing as x plus 2 times x plus 2. It gives me x squared. Outside and inside products are the same. 2x and 2x is 4x, and then 2 times 2 is 4 minus 9. So I've got x squared plus 4x minus 5, and I need to factor that to find my x-intercepts. Well, negative 5, that means my signs are going to be different. 1 plus, 1 minus. 5 is prime. I can just use 5 and 1. The 5 needs to be positive so that when I find that difference, my outside product is negative x, my inside product is positive 5x. That gives me my positive 4x. So to finish finding my intercepts, I take each of these factors and set them equal to 0. That's my 0 factor property that tells me to do that. And I get x-intercepts at negative 5 and 1. So my x-intercepts are negative 5, 0, and 1, 0. Let's see if that works. 1, 2, 3, 4, 5, and positive 1. And look, yeah, I can draw my parabola through those points, and everything's going to hit where it should hit. It looks good. I drew it a little wobbly, but it worked. Okay, I have a minimum value. I can see that I have a minimum value. My parabola reaches a low point. That minimum value is the y value of my vertex. It's how low is my function value. The minimum value is negative 9, and it happens where x is negative 2. That information is found from my parent function. The axis of symmetry is that line through the vertex where I could fold my parabola in half and the sides are going to match. That is a line, so it's a function. Well, it's not a function, but it's a line, an equation of a line. So it has to be x equals, since it's a vertical line. Domain of a parabola is always all real numbers. Range changes according to where my vertex is. This vertex is at negative 9. So my range is from negative infinity up to negative 9. Oh, I said that backwards, didn't I? I start at negative infinity. My parabola does not exist down here. It starts existing at negative 9, and then it exists to positive infinity. You've always got to go from least to greatest values with these intervals. Okay. Let's look at the next one. This one is also in my graphing form. The thing that I notice right off the bat that is different is that I have a negative out front. So my parent function is the same. I still have my parabola. My parent function is still y equals x squared. But this transformed parabola is going to open down because it's got that negative out front. It's going to reflect across the x-axis. Since it opens down, it opens like this, I know that I'm going to have a maximum function value, not a minimum. My vertex is found using horizontal and vertical shifts. I've got 3, 2. So positive 1, 2, 3, up 2. It's going to open down, so I'm going to have real value x-intercepts. This 3, 2 tells me my maximum function value is at 2. The maximum value is 2, and it happens where x is 3. And that vertex also tells me my axis of symmetry. My x value, that line x equals 3, that's going to be my axis of symmetry right there. The line x equals 3. Domain of a quadratic function is always all real numbers, and since we know we have a maximum value of 2, our range is going to be from negative infinity to 2 and stop at 2. Now if you can't get that there until you get your graph finished, that's fine, not a problem. Before I can finish my graph, I need to figure out my y-intercepts and my x-intercepts. My y-intercept happens where x is 0. So I would have y equals a negative 0 minus 3 squared plus 2. This is 9, but this makes it a negative 9. So that is a negative 9 plus 2 gives me negative 7. So my y-intercept is at 0, negative 7. Let's see if that makes sense. It does. We fit that right through there. We still need to figure out what our x-intercepts should be. My x-intercepts happen where y is 0. So I say 0 is 0x minus 3 squared plus 2, and I need to FOIL this, and then I need to distribute that negative through. So it's x squared minus 6x, because negative 3x from my outside and inside products. Negative 3 times a negative 3 is a positive 9, but then I distribute this negative through. So negative x squared plus 6x minus 9 plus 2. Ran out of space. So I've got 0 equals negative x squared plus 6x minus 7. I can't factor anything with this negative on my squared term. So let's move it all to the other side. Let's make our x squared term positive. That's going to change all of those signs. So that's what I want to see about factoring. When I get this over here to see about factoring, I see that my 7 is positive. My 7 is positive, which means my signs have to be the same, and I need to end up with a negative 6 as my middle term. The problem with this is that 7 is prime. If the signs could be different on the factors, this would be factorable, but they can't be. They need to be the same on the factors. So this is not factorable. What do we do to find values for a quadratic equation that is not factorable? Well, if it's not factorable, we have to use our quadratic formula, and that's what we're going to need to do here. You have to know how to use your quadratic formula. You have to have it memorized. I need that squared term to be positive. It helps things out. Negative b here is going to be a positive 6, so x is going to be 6 plus or minus square root of b squared, negative 6 squared, that's going to give me a positive 36, minus 4 times a times c, all over 2a, where a is 1, c is 7. So I've got 6 plus or minus 36 minus 28 over 2. Now I knew that this wasn't going to be a pretty integer value because it's not factorable. It's going to be it's going to be a radical, irrational. I also knew it was going to be real number intercepts because of the shape of the graph. The vertex is up here and it opens downward, so it does actually intersect the x-axis. So I'm expecting two irrational real numbers here, and that's what I'm going to get. 36 minus 28 gives me 8 over 2. 8 is not a perfect square, but I can simplify the square root of 8. So the square root of 8 is the same thing as 4 times 2, right? 8 is 4 times 2, and 4 is a perfect square. So I can break that apart and say that's the same thing as square root 4 times square root 2, and the square root of 4 is 2. So the square root of 8 simplifies to be 2 square roots of 2. So where has that got me? I've got 6 plus or minus 2 square roots of 2 over 2, because square root of 8 is 2 square roots of 2. And then I can simplify all of this by splitting my numerator into two separate terms with 2 as the denominator. 6 over 2 plus or minus 2 square root 2 over 2. Well, 6 over 2 is 3. Plus or minus, anything over itself is just 1. So plus or minus square root of 2. So these are the coordinates, the x-coordinates for my x-intercepts. I've got 3 plus square root 2, 0. And I've got 3 minus square root 2, 0. Now, on my graph, to figure out about where to put that, I want to give my answer in its exact values, 3 plus and then 3 minus square root of 2. But to figure out where to put that on my graph, I'll do 3 plus the square root 2, and I get about 4.4. So that's about 4.4. And then I do 3 minus square root 2, and I get about 1.6. 1.6. So let's see if that makes sense. If I do 4.4, 1, 2, 3, 4, about 4.4, and then I do 1.6, yeah, look at that. That makes sense. My points fall so in a way that I can draw a nice balanced parabola as my graph. So I used quadratic formula to find my exact values for my intercepts. I wrote them in exact terms, but then I figured out, okay, how am I going to graph that? What's that going to look like as a graph? Okay, these were excellent practice problems for how to graph when we start with that graphing form of our quadratic equation. The next two practice problems tell us what to do when our equation is not in that graphing form. When it's in a form other than the graphing form, how do we deal with it? Well, we go back to that quadratic formula that I told you to memorize. Our quadratic formula, x equals negative b plus or minus square root of b squared minus 4ac all over 2a. When it's not in graphing form, we have to find the vertex. Now the vertex is that horizontal shift, vertical shift away from the origin. The vertex is in x, y form still, but x is the horizontal shift, y is the vertical shift. To find that x value, that horizontal shift, whichever way you want to look at that, I don't like the way I wrote that there. So to find the x value, which is my horizontal shift, I'm going to use this first piece of my quadratic function, negative b over 2a, right there, that numerator, that first term in the numerator and the denominator, negative b over 2a. And then to find the vertical shift, the k, or the y value for my vertex, I take this value that I got for the horizontal shift and I plug it into the function and I see what it gets. Because y value is the function value at some x. So I find my x and then I evaluate the function for that value x. Okay, here's how that works. Here we have a quadratic function. It is not in my graphing form, it's in standard form. So I'm going to have to use the method that we just lined out. I'm going to say, okay, my h, or my x coordinate for my vertex, is negative b over 2a. Well, negative b will be positive 4. 2a, a is negative 1. So I have 4 divided by negative 2, which is a negative 2. That's the x, or the horizontal shift. The y value, or the vertical shift, I'm going to take the function value of negative 2. The x value that I find, I plug it into the function. So here's my function, negative, and then I've got negative 2 squared minus 4 times negative 2 plus 5. Well, what does that give me? Negative 2 squared is 4, and then I've got this negative out front, so that's a negative 4. Negative 4 times negative 2 is a positive 8, and then plus 5. Well, 8 and 5 is 13. Minus 4 is a positive 9. So there's my parabola, negative 2, 9. Now, is this parabola going to open up or down? Well, I've got this negative squared term, so that flips it upside down, and it opens down. I've got a vertex at negative 2, positive 9. It's going to be balanced on an axis of symmetry here. X equals negative 2. And I know that the domain of any quadratic function is all real numbers. This parabola opens down, so that value, that vertex, is a maximum. And that maximum function value is 9. That's as high as it goes. And it happens where x is negative 2. That kind of bled together, didn't it? Let's fix that. Happens where x is a negative 2. So my range starts down here at negative infinity. It comes all the way up to this function value 9. So my range is from negative infinity up to and including 9. I know that I'm going to have real number x-intercepts, 2 of them, and I'm going to have 1 y-intercept. Now the great thing about this standard form, my y-intercept's super easy. To find the y-intercept, I plug in 0 for x, so that's 0, and I get 5. 0 minus 0 or plus 0 plus 5 is just 5. So where x is 0, y is 5. There's my y-intercept. That makes sense so far. We're in good shape. X-intercepts happen where y is equal to 0. So let's do that. Let's say, okay, y equals 0. I've got negative x squared minus 4x plus 5. Don't want to try to factor that with that negative x squared. So I'm going to move everything to the other side. They change signs. That becomes plus 4x minus 5 equals 0. That's factorable. 5 is prime, but if I can do opposite signs, this negative 5 means my signs are different. I can do 5 and 1. So I've got a positive 5 and negative 1 gets me a positive 4 there and a negative 5 there. Set each of those equal to 0 and I get my x-intercepts as negative 5 and positive 1. So I take each of these factors, I set them equal to 0 and I finish solving. X plus 5 equals 0, x minus 1 equals 0. I get negative 5 and positive 1 for my x-intercepts. Negative 5, 1, 2, 3, 4, 5, positive 1, and all of those points work together. So I can draw a parabola through them. We are balanced on that axis of symmetry right here. These x-intercepts, this one is 3 units that way, this one is 3 units that way from the axis of symmetry, so we are in great shape there. Okay, and that's all of that one. One more. I want to really encourage you, because all we have left are a couple of application problems. So I want to encourage you to pause the video, see if you can do this one on your own, and then come back to see how you did. We've got standard form. Our parabola is going to open up because that's positive. If we do negative b over 2a, I've got 10 over 2. 10 divided by 2 is 5. That's the x-coordinate of my vertex. Then I find f of 5. I plug it in. Get 25 minus 50 plus 20. Well, 25 and 20 is 45. Minus 50 is a negative 5 for the y-coordinate. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. My vertex is down here. I automatically know some stuff. I know this is my axis of symmetry at x equals 5. I know that my domain for any parabola is all real numbers. Since this opens up and the vertex is down here, it's going to go up. I'm going to have 2 x-intercepts, real x-intercepts, and 1 y-intercept. I know that this is my minimum value at negative 5. It happens where x is positive 5, and since this is my minimum value, my range starts at that negative 5 and goes up to positive infinity. X and y-intercepts are all we have left to get. Y-intercept happens where x is 0, so that's 0, 0, 20. So my x-intercept is going to be way up here. I'm going to have like a break. I can't draw it all the way. So at 20, I have a y-intercept. X-intercepts happen when I set y equal to 0, so I need to factor this. This isn't going to factor right. I'm going to have to use my quadratic formula again. So if I set y equal to 0, I've got x squared minus 10x plus 20. My factors of 20 are going to be 4 times 5 or 2 times 10 or 20 times 1. None of those add up to give me a 10. So I'm going to have to use my quadratic formula here. Negative b is going to be 10 plus or minus square root of negative 10 squared minus 4ac all over 2a. So what have I got? I've got 10 plus or minus square root of 100 minus 4 times 20 is 80 over 2. So 10 plus or minus square root of 20 over 2. 20 is not a perfect square, but it has a perfect square factor. 20 can be written as 4 times 5, and remember the square root of 4 is 2, right? So that could be square root 4 times square root 5. Square root 4 is 2, So square root 20 simplifies to be 2 square roots of 5. So my numerator is 10 plus or minus 2 square root 5 over 2. I can simplify this by splitting it apart. Keep the denominator for both terms. 10 divided by 2 is 5. 2 over 2 is 1. So 5 plus or minus square root 5. Those are my two values for my x-intercepts. Those are the exact values. 5 plus square root 5 and 5 minus square root 5. To go about graphing that, I need to get an approximate value. I want to give the exact value. I need to know the approximate value. 5 plus square root 5 is about 7.2. 5 minus square root 5 is about 2.2. Let's see if that looks like that makes sense. 2.2 would be about here. This is 5, 6, 7.2. Yep, that looks good. That makes sense, so that I can sketch my parabola and hit all 4 of those points in a way that looks like a parabola. Okay, excellent. Okay, again, you are figuring out what questions you know, what you understand, what you don't, so that you know what you want to ask about in class. Or talk to a tutor about if you're not going to see me in class. Alright, application problems. A bullet is fired upward from ground level. Its height above the ground in feet at time t seconds is given by this function. Now this constant here, -16, we get because gravity is going to pull that bullet back down, right? If we, and ground level just makes it easy. If we think about a bullet, if you fire up, that bullet's going to go up, but then gravity is going to pull it back down, and it's going to come back down and somewhere hit the ground over here, right? So there is going to be a place where we have a maximum height achieved. Find the vertex. Well, that vertex is going to give me my maximum height of the bullet. The vertex is going to be -b over 2a. We're going to use our quadratic formula. Well, this is b, so that's -960 over 2 times -16. Um, 960 divided by 32, that's going to go in 30 times. So it's going to get up, it's going to move over 30. T is my input, that's 30, so that's my, and then my height in feet, time in seconds, height in feet. So at 30 seconds, my bullet has reached the peak of its trajectory. How high up did it go? Well, 30, and then I plug that in, -16 times 30 squared plus 960 times 30. I use my calculator to help. 30 squared first, and then times a -16 gets me -14,400 plus 28,800. Tells me the bullet went up 14,400 feet. That's my vertex right there. So at what time did the bullet reach its maximum height? It reached that height 30 seconds after it was fired. I know that because my input t is time in seconds. What is the maximum height? Well, it's that maximum height we found for the vertex, 14,400 feet. That's how high it reached at 30 seconds after being fired, and then after that point it fell. Find the time at which the bullet hits the ground when the height is equal to 0. So at time 0, it's at the ground level, and then at the end of its travel, it's at ground level. That is going to be height, so y value equal to 0. So I set my equation equal to 0, and I'm going to solve. I don't have a constant here, so I can factor out a common factor between 16 and 960. If I divide 960 by 16, I see that it goes 60 times. So 60 times 16 is 960. So if I factor out, and I'm going to factor out that negative as well. If I factor out that -16, and then I can also factor out a t, because I've got a t squared and a t. So -16t is going to leave me t minus 60 here. So my two factors, 0 equals negative 16t, and 0 equals t minus 60. Well, to solve this, anything divided by 0 is 0. This gives me my initial place where the height of the bullet is 0, when t equals 0, 0 seconds when we fire the gun. And then when we are at 60 seconds is when it comes back down. Does that make sense? Well, yeah, because it's a parabola, so it should be balanced. So if at 30 seconds it's reached its maximum, then at 60 seconds it's back down to the ground. Alright, last example here. A store owner finds that a price of P dollars, X units of a certain item will be sold. The demand is given by this function. So at a price, we sell X units. Now recall that the revenues are price times quantity. So our revenue function is going to take this price function. This is my price function times quantity, so times X. So my revenue function takes price, 84 minus 2x, times X. So I get 84x minus 2x squared. That's my revenue function. Is that a linear revenue function? No, it's not linear. I know that it's quadratic, so it's going to be a parabola. It's parabolic. It's not going to graph like a line. It doesn't. My revenues don't keep going up no matter how many I sell. My revenues are going to be a maximum and then they're going to fall again. And I know that they're going to fall again because it is negative squared term. So it has a maximum revenue before the revenues start to fall. How many items are going to lead to a maximum revenue? Well, that's my input, my negative b over 2a. Now, to do negative b over 2a, I need to take this formula and I need to put it in the right order. My revenue function, r of x, in the correct formula to use as a quadratic formula, it would be negative 2x squared plus 84x. So negative b is going to be negative 84, 2 times negative 2, as 2a is my denominator. So 84, negative 84 over negative 4 gives me a positive 21. That's the number of items I need to sell for maximum revenue at a certain price. What is that maximum revenue? Well, I plug that number x into my revenue function. So I'm going to get maximum revenue when I sell 21 items. Order of operations, 21 squared times negative 2 gives me a negative 882. 84 times 21, 1,764. I get a maximum revenue of $882. So when I sell 21 items, I get a maximum revenue of $882. Now, is that profit? No, that's the total you can bring in, but that is not the same thing as profit.